Courses in the cement industry. Present to you. Electrostatic precipitator. In this course will be explained electrostatic precipitator types, working principle, and dust precipitation rule. An electrostatic precipitator, ESP, is a particle control device that uses electrical forces to move the particles out of the flowing gas stream and onto collector plates. The particles are given an electrical charge by forcing them to pass through a corona, a region in which gaseous ions flow. The electrical field that forces the charged particles to the walls comes from electrodes maintained at high voltage in the center of the flow lane. Once the particles are collected on the plates, they must be removed from the plates without re-entraining them into the gas stream. This is usually accomplished by knocking them loose from the plates, allowing the collected layer of particles to slide down into a hopper from which they are evacuated. Principle of electrostatic precipitators. The principle of dust collection with electric precipitators, also called electric gas cleaning, or electrostatic precipitation, is based on the utilization of the effect of gas ionization in a strong electric field, which is formed by discharge electrodes, corona effect, negative, and by collecting electrodes, positive. With a sufficiently high electrical voltage between the two electrodes, high voltage DC, of about 40,000 to 80,000 voltage, the discharge electrode begins to emit electrons, resulting in charging the gas molecules surrounding the electrode in positive and negative ions. Under the influence of the strong electric field, the negative ions now migrate to the grounded positive, or collecting electrode. If the gas is dust-laden, the negative ions impose their charge onto the dust particles, which then are attracted by the positive electrode, being here precipitated and neutralized. By wrapping or vibration, the collected dust is removed from the collecting electrode, dropping into a dust bin. However, a small part of the dust particles will also be charged positively, and precipitate on the discharge electrode. Therefore, for cleaning, the discharge electrode must also be wrapped. Consequently, there are the single procedures, which are decisive for electrostatic precipitation: corona effect, particle charging, and particle precipitation. We flowing with us. Principle of electrostatic precipitators. Depending on the conception of the gas, its temperature, and the nature of the dust, it happens that the attractive force of the collecting electrode slows down, resulting in a lower efficiency of the electric precipitator. In this case, the deciding factor is the electrical conductivity of the dust, which should be between that of a good electrical conductor, metal, and that of a good electrical non-conductor, porcelain. However, not too close to either extreme. To define this characteristic, the opposite of the electrical conductivity, the electrical resistance, is applied. For the most favorable precipitation conditions of an electrostatic dust collector, the electrical resistance of the dust particles should be between 10/4 and 10/11 centimeters, ohm. The electrical resistance of most kinds of dust appearing in a cement plant is within these limits. Dust with a low electrical resistance loses its electrical charge immediately on the collecting electrode, and after reversing polarity, returns into the gas current. We flowing with us. Principle of electrostatic precipitators. The electrical resistance of the dust increases with increasing temperature, with an electrical dust resistance in the magnitude of 10/14 centimeters, ohm. The dust adheres to the collecting electrode, forming an insulating layer, thus considerably deteriorating the rate of precipitation. In this case, spark points appear on the collecting electrode, generating reversed ionization. The remedy for this condition is moistening of the gases, to increase the conductivity of the dust particles. In other words, it can be said that a higher moisture content of the carrier gas lowers the electrical resistance of the dust. Therefore, manufacturers of electrical precipitators recommend a moisture content for rotary kill exit gases of 15 to 18%, by volume. This necessitates the application of spray towers, or evaporative coolers, which increases the investment and operating costs. Electric precipitators for clinker cooler, vent air on the other hand, show the highest efficiency with vent air moisture of only 2.5 to 3.5%. By volume with a gas temperature close to the dew point, the influence of the moisture is more effective. This results in a better degree of precipitation. In this picture it is explained. Shows the working principle of an electric precipitator. See this video.
Principle of ESP. When flue gas with dust particles is passed through a high voltage of electrostatic fields, electrons are released. The high voltage current is passed through the anodes. The leakage of current from the anodes is called corona. These electrons charge the dust particles negatively. The negatively charged particles sticks to the cathode. This process is called collection.
In this picture it is explained. The diagram illustrates the mechanism of a corona discharge. In this video it is explained. Electrostatic precipitators, operational principle. Collecting and discharge system principle. Shown with type Fibulax discharge electrode, could be type helical. The red color symbolizes discharge system. The blue color symbolizes collecting system. The collecting and discharge system consists of 1. Supporting insulator. 2. Casing. 3. Supporting beam for discharge system. 4. Supporting iron for collecting plates. 5. Discharge electrode fibulax, or helica, helical always to each plate. 6. Collecting plates. 7. Tumbling hammer. 8. Wrapping bar. Types of electric precipitators. There are two fundamental types of electric precipitators. 1. Duct, tubular collection, type precipitator. The duct-type precipitator is shown in this figure, and serves mainly for cleaning gaseous suspensions. To reprocess the precipitated dust, in the manufacturing procedure, the cement industry employs only dry electrical precipitation, for this purpose. 2. Plate-type precipitator. The plate-type electric precipitator is in use, see figures. In addition to precipitation by action of the electrical field, there is in the electrical dust collector, also precipitation of a certain quantity of dust particles, by actions of gravity as well as precipitation, by change of direction and by impact. We follow together. Types of electric precipitators. When eliminating the energy supply or during blackouts, the electrical precipitator works as a dust settling chamber, with collection efficiencies of about 30 to 70%. Therefore, collection efficiencies of about 95% are attainable, even under unstable electric conditions. Because of the high mechanical collection efficiency of 85 to 90%, a combination of an electric precipitator with a primary dust collector will be in many cases unnecessary. However, with higher dust concentration, the use of a primary collector can considerably improve collection efficiency. The characteristics of the dust anti-carrier gas are of great importance for the operation of an electric filter. The velocity with which the dust is attracted by the collecting electrodes, traveling velocity, is of importance for the collection efficiency, and depends on the corona voltage, the intensity of the electric field, the dust particle size, and on the viscosity of the gas. We follow together. Types of electric precipitators. The electrical dust resistance increases with increasing temperature, and reaches its maximum at 200 to 258 degrees C. However, above this temperature, the electrical dust resistance starts to decrease. Regular precipitator operation can be attained, with electrical dust resistance up to 10/11 cm, ohm. With an electrical dust resistance higher than that, for example about 10/14 cm, ohm, the dust acts as an insulating layer, which impairs the collection efficiency. In some cases, a temperature change of about 10 to 28 degrees C has a decisive influence on the collection efficiency. Electrostatic precipitators, with gas conditioning tower. 1. Dust particles emitted during different manufacturing processes have a specific electric resistivity, which can be as high as 10/14 ohm centimeter. 2. High resistivity dust is difficult to remove from the collecting electrodes, and often, it may cause a detrimental operating condition, known as return throw of sparks or as back ionization. This condition is generated in connection with a low dew point, and a detrimental gas temperature shows in figure, a collecting electrode with a deposited dust layer. Therefore, dust resistivity is considered as one of the most important operating parameters. 3. From experience it is known that the electrostatic precipitator attains its highest collecting efficiency at a resistivity of the dust particles between 10/4 and 10/11 ohm centimeter. See this video.
Nice example of a coal-fired power station, a thermal type power station. Our coal would actually be stored in these two areas here. We've actually got a roof on this area, so it's under cover. That means that our coal stays dry. We're going to draw it out through conveyors, and then we're going to come along here, away from the storage area, up our inclined conveyor, and then into the boiler house or the power station. It's going to go into our boiler. That's our water tube boiler. It's going to come out. You can see here's one of our ducts that we saw earlier. It's going to pass into this item. Looks a bit like a Lego block or 4 blocks put together. And these items are our electrostatic precipitators. After that, the exhaust gas comes out, comes along here, goes to our flue gas desulfurizer, or FGD. We've also got a video about that if you want to check that out. And then finally, it will go to our cooling tower, which we've also got a video about, and the exhaust gases will be blown out of the top. You can actually see here, there's the pipe connection, and we'll discharge the exhaust gases out of the top of the cooling tower and into the atmosphere. By the time the exhaust gases are discharged from the cooling tower or via a stack, they're actually quite clean. They have to be because, as I mentioned before, people don't want to be made sick if they're living near a power station, and we don't want to damage the environment either. So how did we clean up our exhaust gas? Well, we removed the particulates that are contained within the exhaust gas using our ESP. So the fly ash was removed by the ESP. Usually the ESP is about 98 to 99.9% efficient. It's going to remove a lot of fly ash. We put the ESP before our induced draft fan because all of those particulates then don't need to pass through the fan, which may cause damage to the fan, prior to being discharged. So how are we removing 98 to 99.9% of all fly ash from the exhaust gas stream? Well, let's go and have a look now at how electrostatic precipitators work.
We follow together. Electrostatic precipitators, with gas conditioning tower. This resistively can be reduced by several factors, of the 10 power through water injection, into the evaporative cooling tower, which considerably improves the conductivity, within the electric precipitator. The size of such a conditioning tower is determined by, the gas volume and by the gas temperature, at the entry and exit. Here, the most important parameter, is the specific number of evaporation. See figure. The diagram of specific evaporation numbers. For cooling of exit gases in an evaporative cooling tower for various entry and exit gas temperatures, this diagram is a compilation of the KHD. For example, it lies between 16 to 22. For gas cooling from 350 down to 1508 degrees C, and between 24 to 28. For cooling from 450 down to 1508 degrees C. M3 refers to the effective space for evaporation, within the cooling tower. The arrangement of the conditioning tower in a cement plant, using the precalcining process is determined by, the type of the raw grinding system. If a roller mill is installed, the cooling tower should be located, for practical reasons, in front of the kill ID fan, because at low moisture of the raw material, the total heat content of the exhaust gases, is not needed, but the total gas volume, for material transportation is necessary. If the roller mill is not in operation, when operating without utilization of the exit gas, the total gas conditioning takes place in the evaporative cooler. If for drying grinding purposes a ball mill is installed, then the conditioning tower is placed parallel to the grinding system. This partial gas operation allows the conditioning of small gas volumes, since in this case, the total gas volume is not needed for drying purposes. We follow together. Electrostatic precipitators, with gas conditioning tower. The water injector nozzles of the conditioning tower have a turn-down ratio of 1 to 10, and the volume control is stepless, using a motor-operated control valve in the return line. The dust precipitated inside the spray tower is extracted by a paddle screw conveyor. Depending on the negative pressure conditions, a double flap gate or a self-cleaning rotary valve is installed as an airlock. When using a gas conditioning tower, the efficiency of the electrostatic precipitator is increased, due to higher voltage and ampere levels. Remarks on gas cleaning. The resistivity and cohesivity of the dust are important factors for preventing collected dust from falling back into the gas stream. Coherency plays particularly a vital part in keeping the dust together when it is removed from the precipitator. If the particles of dust do not cohere, they separate and mix with the gas once more, spoiling the action of the precipitator. Dust precipitation rule. The general rule of dust precipitation is to divide the two components of a mixed system in each of them. This means, according to the second law of thermodynamics, to bring this system from a low to a high degree of order. In nature this is only possible by an input of energy. No dedusting equipment can work without the consumption of energy. The relationship between electrostatic precipitators' efficiency, sizes, and power input. Efficiency of electrostatic precipitators. Deutsche formula. We follow together. Deutsche formula. Effective migration velocity, EMV, is related to the rate at which a particle makes its way toward the collecting electrode under the combined influence of the electrical and aerodynamic force on it. 1. EMV is best at a gas of velocity, 2 meters per second, and increases with the distance between the electrodes. 2. Discharge called flashovers. 3. Re-entrainment, plus scouring, depend on gas velocity, must be kept as low and uniform. 4. Puffing, due to wrapping and re-entrainment. Electrodes are wrapped before the layer of dust is thick enough to let the dust fall as a mass into the hopper. Stokes' law. Electrostatic force on the particle equals viscous drag. Cross-section in electrostatic precipitators filter. See this video. A dry electrostatic precipitator, ESP, electrically charges the ash particles, and imparts a strong electric field in the flue gas to collect and remove them. An ESP is comprised of a series of parallel, vertical metallic plates, collecting electrodes, forming lanes through which the flue gas passes. Centered between the collecting electrodes are discharge electrodes, which provide the particle charging and electric field. The figure shows unchanged arc particle collects charge over a wide angle. The figure shows partially charged particle collects charge over a smaller area. The figure shows fully charged particle repels further charge. The forces that occur in the electrostatic precipitator filter. The figure shows the forces that act on a charged dust particle inside an electrostatic precipitator. 1. Aerodynamic force. 2. Force of gravity. 3. Electrostatic force. 4. Result of electrostatic force and gravitational attraction. The figure shows type of the discharge electrode. 1. Rod with special spikes. 2. Wire with star cross section. 3. Flat with spikes. 4. Wire thickness, 2 or 3 mm. Discharge electrode. Fibulax type V. Consists of 1. Flexible point. 2. Oval cross section. 3. V emitter, others U. 4. Reinforcement. 5. Collecting plate. 6. Fix point. This point depending on the ESP height 1 or 2 layers. Collecting system, wrapping systems. The wrapping bars for the collecting plates are made of heavy flat bars. Between the flat bars specially shaped cross members are inserted, one for each collecting plate. At the impact end of the wrapping bars, a specially shaped hardened impact anvil is fixed. The wrapping bars are supported by a bearing bridge and a wrapping bar guide respectively, and there are no fixed connections between the collecting plates and the wrapping bars. The level of the wrapping bars can be adjusted in the supports. The collecting plates are protruding through the wrapping bars, and because of the eccentric suspension of the collecting plates, each plate will press against the specially shaped cross members of the wrapping bars, thus resulting in efficient contact for transmission of impact energy. Individual heat expansion of the collecting plates is allowed by the clearance between wrapping bars and collecting plates, without vertical movement of the wrapping bars. As the wrapping bars do not move vertically, irrespective of the varying temperatures in the precipitator, the tumbling hammers accurately hit a precalculated point on the bars, thus obtaining uniform transmission of maximum impact energy. The tumbling hammers, the weights of which depend on the height of the collecting plates or the process, are made of drop-forged hardened steel, to prevent forging at the impact point. Because of the fixed position of the wrapping bars, and due to the tumbling hammers hitting a precalculated point, it is ensured that no reactions occur in the center of rotation of the hammers, thus reducing wear to a minimum. We follow together. Collecting system, wrapping systems. The total patented wrapping mechanism ensures maximum wrapping efficiency of the collecting plates, as well as long life of the various components. The tumbling hammers are mounted on a shaft, each hammer being turned approximate 30 in relation to the preceding hammer, ensuring that only a few hammers hit at the same time. The turning interval of the hammer shafts is controlled by a timer unit. The shafts, which are equipped with necessary expansion couplings, rotate in heavy cast iron bearings. Shaft with bearings are mounted in the bearing bridge, which also serves as a gangway. The bearing bridge, which is made of heavy L-sectional steel, forms a very rigid unit, suspended from the side walls of the precipitator in laminated springs. This design prevents damage to the wrapping mechanism, in case of deformation of the precipitator casing, such as buckling due to heat or explosions. Electrostatic precipitator. The diagram shows how the dust is distributed inside a precipitator when the gas flow has finite turbulence. The effect of the turbulence is to carry dust in the direction of the concentration gradient. The result is that, no matter how long the precipitator is, the gas in the middle of the duct is never quite clean. The diagram shows dust distribution inside the electrostatic precipitator. Gas flow is laminar. The diagram shows how the dust is distributed inside an electrostatic precipitator when the gas flow has infinite turbulence. At any point along the length of the precipitator, the dust burden is the same all across the duct. The diagram shows. The graph indicates the trend of effective migration velocity with dust resistivity. Dust of low resistivity loses charge as soon as it touches the collecting electrode. It may even recharge with reverse polarity, so that it is hard to collect and the associated effective migration velocity is low. Dust of high resistivity is also hard to collect, because back ionization occurs, and disrupts the operation of the precipitator. The values of effective migration velocity, given in the graph, are indicative only. The diagram shows. Automatic power supply controller. 1. Spark. 2. Arc. The diagram shows. Required dedusting rate, according to a raw gas dust content of 100 gram per cubic meter. The diagram shows. Current flow in the layer of adapted humidity. The diagram shows. The relationship between wire diameter for discharge electrode and corona start voltage. The diagram shows. The charged particles are now forced by the electrical field to move to the collecting electrodes. The diagram shows. Migration velocity, specific collection area depending on the gas temperature. The diagram shows. Dynamic viscosity of gases, and heat dilatation factor. Circuitry associated with precipitators consisting of 1. Isolating switch. 2. Fuse. 3. Main circuit breaker. 4. Current transformer. 5. Thruster module. 6. Current limiting choke. 7. High voltage step-up transformer. 8. High voltage rectifier. 9. High voltage choke. 10. High voltage element. 11. Measuring converter. 12. Automatic voltage regulator. Thank you for watching, and I hope these courses are helpful to everyone. Subscribing to this channel Cement Industry Courses would be appreciated. Thank you.